The induction principle has also a slightly different formulation. This is referred to as the second induction principle. And depending on the property that you want to establish, this might be in fact very useful. And I'm going to have an example for you in a couple of minutes. So the second induction principle has this formulation. You deal with a parametric property P of n, and the induction basis is the same as before. You have to show that you start from solid ground. You have to show that P of 0 holds. So you have your property satisfies P of 0. And the second condition that your property satisfies is of this form. Not only that P of n holds like we had before, but in fact P holds for all the values of the parameter up to n. So it holds for P of 0, P of 1, all the way to P of n minus 1 and P of n. If it holds for all of these, then P of n plus 1 holds. So that's the second condition. And so what the lemma says, if you have a property P in such a way that condition 1 is satisfied, condition 2 is satisfied, then P of n holds for all natural numbers n. So if we think about the comparison with the first induction principle, the induction basis is the same as before. You still have to show that P of 0 holds. The induction step, the idea is the same. You will have to step up from n to n plus 1. The fundamental difference here is that the induction hypothesis is more complex. You take you take a more complex induction hypothesis in this formulation of the induction principle. So your induction hypothesis is that P of n holds, P of n minus 1 holds all the way to P of 0. And you can use all of these properties in establishing P of n plus 1. So that's a more complex, a more powerful induction hypothesis than we had before. So if you have that both the induction basis holds and the induction step holds, then P of n holds for all n greater than or equal to 0. So I want to prove this for you, and the way I'm going to do this is I'm going to in fact apply the first induction principle. So I'm going to do it like this. I'm going to define a property, so define property S in the following way. I will say that S of n holds if and only if P of 0, P of 1, and P of n hold. And I'm going to prove that S of n holds for all natural numbers n. And obviously, as a consequence, by the way we have defined S of n, if S of n holds for all n, then in particular P of n also holds. So that's going to establish our lemma. So the aim is going to be to show by induction that this property we have defined here holds everywhere. And so as usual, what we do is we are looking at the induction basis. And that means that we have to check that S of 0 holds, but S of 0 by definition, so S of 0 holds if and only if, and this is by definition, if and only if P of 0 holds. That's just how we have defined here our property S. And this is in fact which is true by condition 1. So the induction basis is thus established. S of 0 indeed holds. And for the induction step, we will say, let's assume, so I'm going to say assume our induction hypothesis is going to be that S of n holds. So this implies, by definition, by the way we have defined S of n, that in fact all of these hold, P of 0, P of 1, and all the way to P of n, they also hold. And this implies now by condition 2 in our lemma that P of n plus 1 holds. And so what this implies now, by definition, in fact, we will have that all of these hold. So P of 0, P of 1, P of n hold, but also P of n plus 1 holds. And if you look at how we have defined our property, that's exactly the same as S of n plus 1 holding. So this implies by definition that P of n plus 1, I'm sorry, S of n plus 1 holds. And so now we can apply the induction principle for property S and conclude that the property S holds for all natural numbers n, and as we have discussed, this implies right away that P of n holds for all natural numbers n, and that establishes our result. So just to summarize this second induction principle, it's very similar to what we had before. The only difference is that the induction hypothesis is somewhat more complex, and there will be cases where you will need this kind of more complex induction hypothesis, and it just says that, you know, the induction hypothesis assumes that the property holds for all the values of the parameter up to n, whereas before in the first induction principle it was simply that P of n holds. You didn't assume anything about the earlier values, but here you say P of n holds as well as all the smaller values of the parameter, and using that you are aiming to prove in your induction step that P of n plus 1 holds. And as a matter of fact, this second induction principle has a similar formulation also for a higher basis. So the induction basis doesn't have to start from 0, it can start from a number greater than or equal to 0. So we can also have the induction basis to be that P of n 0 holds, and the induction step, just the same as before, it holds for all the numbers starting from n0 to something like n0 plus n, and if they hold, then the next one also holds. P of n plus n0 plus n plus 1 holds. So if you have properties where these two conditions are satisfied, then P of n holds for all values of the parameter greater than or equal to n0. So this is exactly the same as the formulation we had on the previous slide. The only difference is that you don't start from 0 with your property, but you start from a higher basis. And we had this discussion for the first induction principle, so by now I guess that this could be quite familiar to you. So the proof of this result is going to be in this week's exercises, so I don't cover it in this lecture. But I want to show you an example where, in fact, this second induction principle is very useful, and you would have a hard time proving the property using the first induction principle. And so the example I want to show you is this. I want to prove that any natural number greater than or equal to 2 can be written as the product of prime numbers. And we will prove this by using the second induction principle. Obviously, first we do the induction basis. And so the result we are aiming to prove says something about numbers starting from 2. So obviously our induction basis is going to be 2. And so the induction basis is simply to establish that 2 is the product of prime numbers. And this statement is obviously true because 2 itself is a prime number, and obviously you can write it as a product containing just one single factor itself. So this is a trivially true statement. 2 is indeed a product of prime numbers with the product consisting of just one factor. So this is true, the induction basis. And now for the induction step, what I'm going to do is I'm going to use the induction, the second form of the induction principle, and I'm going to assume that the property is true or holds for all numbers, and the stress here is on all numbers up to n, or smaller than n, I should say. So I'm assuming this form of the induction hypothesis, that the property holds for all numbers smaller than n. So any number smaller than n can be indeed written as a product of prime numbers, and I want to show the property for n. And so I'm looking at n, and there will be two different cases. One case is when n is a prime number. Now, if n is a prime number, then the property is trivially true. Being a prime number, it means that it is indeed a product of prime numbers, and again the product is just trivial. It has only one factor, and that's n itself. So the property is true. There is nothing to prove here. And the other case is n is not a prime, n is composite. And in fact, what this means is that I can write it as the product of two smaller numbers, n1 times n2. And obviously n1 is smaller than n, and n2 is smaller than n. And the point here is that I'm just going to continue here. The point here is going to be that I can apply induction hypothesis. So and I'm going to apply it to this n1. n1 is smaller than n. It's probably not a predecessor of n. It's a number that could be quite much smaller than n. So that's why this formulation of the induction hypothesis that the property holds for all numbers smaller than n is going to be very handy in here, because I can apply it to n1 without worrying how much smaller than n this is. So by induction hypothesis, n1 can be written as the product of some prime numbers with pi primes for all these i's. And in fact I can do the same also for n2. n2 is also smaller, and so this also can be written as the product of some small prime numbers. And so there we have it. Since n1 and n2 they are this product, then obviously what this implies is that n, because n is n1 times n2, is exactly this product of prime numbers. It's p1 times pr times q1, all these numbers multiplied all the way to qs. And so there you have it. We have that n is a product of prime numbers. So we have established in this way the induction step, and this means now that we have established that our property holds for all numbers greater than or equal to 2 by applying the second induction principle.